All right, so we're still having network problems, so let's go on to the next one. We're going to talk a little bit about C++ testing. I'm going to laugh if I don't have that tool either, which is quite possibly the case, but that's all right. We have testing, more into pointers, and then OOP with C++. So you did a pointer lab, and now we're going to do even another pointer lab, because pointers, if you don't get them, you're not going to pass this course. All right. So objects are going to be very similar to Java, namely because Java based their way of doing objects on the way C++ did them. Although I should really say Java and C++ based their objects on Smalltalk, so they share a common ancestry, I guess is the best way to put it. The difference is C++ allows multiple inheritance. We're not going to do that in this class because I don't care, which means there's no need for an interface keyword. Templates inside of C++ are going to act as generics, and we will be templating a lot of our code inside of for this class, just so it enforces the fact of a generic algorithm. But keep in mind that C++ is compiled to machine code, Java compiles to bytecode. The reason for that is templates are going to be a compile time construct. Once your code is compiled, templates are gone. They're no longer there. As opposed to Java, when it was compiled to a bytecode, your generic still existed until you started running. All right, testing. How many of y'all like testing? How many of y'all have done testing? Ooh. Did y'all like it? No? All right, well, unfortunately, testing makes you more productive. That's the sad news, so you need to do it. It means you're actually going to spend less time on your problems if you actually write some of your tests. If you start having issues with the program, start writing some tests and put it like a battery of test cases and start running them. It's actually going to help you in the long run. Also, if you actually write your test first, it increases your chances of getting it done the right time. And let's see. And virtually never make the same mistake twice. By the way, which one's easier? Writing the code the first time or trying to fix its problems? Writing it, which one? Writing it and then trying to fix it takes longer?
It depends.
It depends. Unfortunately, that is not it depends. Usually it does take a lot longer to try and fix it than writing it the first time. All right, proven fact, a computer program cannot sufficiently generate test cases for your code. Oh yeah, that's actually a big issue. Why is that a big issue? By the way, when I say proven, I mean Turing wrote a proof that shows beyond the shadow of a doubt that it's impossible for a computer to determine if a program halts. Why does this matter? Because if we can't tell if a program halts, then we can't really test everything, because we can't test if your program finishes. But why is that a problem? Well, wouldn't it be nice if we could hit a program to generate the test cases for us? Right? Yeah. Can't be done. Did y'all want to see the proof of that? Or are we tired? This is always the funniest part, because if you want to see the proof, I'm going to go to YouTube and watch a YouTube video while I'm recording inside of a class that I'm going to push back up to YouTube.
Inception.
Yes. Tired? I mean, this is your time to watch a video, right? Okay. Let's see if I can do this. YouTube halting problem. Oh, I wonder how loud this is going to be. Or it may not. Oh, there it is. Oh, we get to have an ad? Nice. I don't have an ad blocker. Oh, I skipped it.
At least it's an appropriate one.
Yes, that's true. Ooh, we don't have sound.
That's a problem.
Let's see if I can give you sound. It's not there. Not there. Oh, no sound for you? Ooh, you may not be able to get sound. It's coming out. Wait. Huh? That's this one. Let's play back.
prints the answer.
Nice.
It always prints the right answer.
It always tells you the right answer. That's sweet. All right. I cannot tell how loud this is. Too quiet, too loud?
It's okay.
There we go. By the way, if you do not fully understand this, that's okay.
This is computing machine A. A solves problems in arithmetic.
We have computers that do that, don't we?
It
You know,
receives
they
a
add.
problem written on paper.
They're really good at
and
adding.
it prints the answer.
Really good at adding. I just wonder if they do that
It
generally.
always prints the right answer. Here's another computing machine, C. C plays checkers. It receives the current state of the board, and it prints how it would move one of the red pieces. C plays checkers so well, it will never lose a game.
That program exists too. You can write a program that will never lose in checkers.
A and C are machines we can already build today, and computers keep getting smarter and smarter.
I don't know what that word smarter means, but you know, whatever.
Let's feed A with a board of checkers. A was not designed to handle this kind of input.
Because that was doing the arithmetic. A was doing arithmetic. So it gets stuck when it tries to do checkers. All right. But again, I just wonder if they could put them next to each other and make a race.
This blueprint is detailed down to the level of the logic circuit, and it fully defines how A works.
You'll be able to draw all that in architecture, by the way.
We are now finally ready to introduce a marvelous machine called H.
Ooh,
H solves what is known as the halting problem. It can analyze the blueprint of another machine and determine which inputs are good for it and which will cause it to get stuck.
Does that make sense?
It receives the blueprint of the machine to be tested and an input to test it with. Based on the blueprint, H simulates the given machine on the given input, and then determines if it gets stuck or not. H solves the halting problem perfectly. It always prints the right answer.
So obviously, if that was running, it would get stuck.
Here are
Okay.
2 more examples with the blueprint of the checkers machine.
Yeah, so it does checkers. Look at that. And it's going to be stuck. All right, we're doing great.
H is a nice machine, but can we really build it? We'll now prove that its very existence is logically impossible.
So we can't do that. It's not that it's a hard problem, it's impossible. By the way, anyone have an idea about how we're going to do that? So it's going to be a proof by contradiction. So we're going to assume that it exists and then show that that is not possible for it to exist, which is a very powerful tool.
Let's assume that H does exist.
So it's going to be proof by contradiction.
We'll place it on this stand for reasons that will be made clear in a minute. Recall that we assume H solves the halting problem perfectly. It
Right.
should always print the correct answer. We are about to put this to the test. This is a photocopying machine. It simply prints 2 copies of its input.
Does that program exist? That program exists. So P exists, right? We know P exists. So we're going to put that around on top of it. Great.
Here's another simple machine. We call this one the negator. When the negator receives the words not stuck, it gets stuck. And when it receives the words stuck, it does not get stuck. And
just
it prints
press.
a smile.
Can we write that program? If not stuck, go in infinite loop. If stuck, print smile. Right? That program is there. So P and N exist. We know that P and N exist. All right.
Let's wrap it all in a neat package we call the X machine.
The X machine.
X
All right.
has one input and one output.
All right. So hold on. This is where people start to get a little lost. So the X machine is composed of three machines, right? The photocopier, the halting machine, and the negator. We know that the photocopier and the negator have to exist. So if we can prove that the X machine doesn't exist, then that means that the halting machine can't exist because those other two ones exist. Everyone good? That's usually where students get lost. Are we good so far? All right. So how are we going to prove it?
Blueprint.
Oh, so they're going to rephrase it. That's nice.
As before, this blueprint fully defines X.
All right, what are they doing?
What do you think will happen if we feed X with its own blueprint? Will it get stuck?
All right, hold on a second. This is the most classic thing to do in computer science, and actually in most things. If you want to test it, throw it in on top of itself. Like when you write a compiler for C and you write it in C, what's the first thing you compile? The compiler. This is a very classic thing to do. Probably should always be your first test. If you can throw itself, or it's called dog fooding actually, but I don't know why it's called
Because
dog.
it's nasty.
It's nasty, sure. I don't know why they call it dog fooding, but that's what it's called. You just first test, take what you have, send it to itself, see what happens.
Call it literally anything else.
Yeah, you could.
Call it flush.
I think they call it dog food because it's eating its own dog food, for example. You know, that's cannibalism. Anyways, we're going forward.
Surprise.
All right.
B simply duplicates our input.
Right, so that happens, no problem.
H receives two copies of the blueprint of X.
There's two things it can do, right?
Determine what happens when X is fed with its own blueprint.
It can do one of two
Let's
things.
assume it says not stuck.
So it's not going to be stuck because it said that X isn't going to be stuck.
Negates that.
But we put that in the negator. And what's the negator do?
So feeding X with its own blueprint causes it to get stuck. But H said it wouldn't. H was wrong.
Do y'all see that? So H says X is not going to get stuck, aka itself. So it says it's not stuck. But since we sent it to the negator, it got stuck. That's a contradiction. So therefore, this can't happen. So it can't predict not stuck.
Let's try again.
Let's do the other thing. Let's pretend it says stuck, right?
This time, we'll assume H says stuck.
Totally stuck. But we send that to the negator, and what does it do?
Not stuck.
It's not stuck. Uh-oh.
X didn't get stuck. But H said it would. H was wrong again. But H is supposed to always be right. This is a contradiction, proving H cannot exist.
So condescending.
Got this. Oh, it even has the nice QED. All right. If you don't get all of that, that's okay. But hopefully most of that made sense. Did that make sense to most of y'all? Maybe some of y'all? Usually about half the class, a little over half gets it. So if you don't get it, don't feel bad. It'll make more sense when you take algorithms. All right, so the Turing wrote a proof in the 30s. That's 1930s. And if we can't halt, then how can we test? So we have to do the tests ourselves. And actually, this is a huge advantage we have over our machines. All right, unit testing is sufficient. Did y'all do JUnit in Java? All right. So there's many forms of testing, but we're going to just stick with unit testing here because it's the most simplistic and it's basically all we're going to need for the assignments we're doing in this class. There are numerous unit tools. but no de facto standard for C++, which is quite unfortunate. Because the nice thing about Java is if you want to do unit testing, just use JUnit. Everyone uses JUnit. We're happy with JUnit. JUnit works. In C++, we do whatever. I chose CSX TestGen for this class. You, of course, can choose whatever you want for your labs. I'm not testing your test cases, but in the background, the autograder is using CSX TestGen. Okay. So let's see if I have this thing. I do have it. Great. Oh, for testing. And do I have an example? No, I don't. Okay. Oops. So, I really wish I uploaded my testing code. All right. Hang on a second. We're going to pause for a moment.